Hello and welcome to another lecture of electromagnetic field and waves. This is lecture 20. I just spent a couple of minutes discussing what we did last time. So if we just quickly review. So last time we basically discussed the reflection and transmission of electromagnetic waves when they are incident at normal incidence on a dielectric barrier. So essentially the idea of what we did was that you have an interface here, and this is an interface between a material of refractive index n1 and another material of refractive index n2, and you have some incoming electromagnetic radiation which we denote here. So it's some incoming wave vector ki, where I stands for incidence. You have some reflected wave vector going back, which we denote kar, and you have some transmitted wave vector ki. Okay, and given this scenario, we calculated how much of the light is transmitted and how much of the light is reflected. And in the end, what we calculated were these transmissivity and reflection coefficients, where the transmissivity T was the amount of electric field that's transmitted, Et, over the amount of electric field that was incident, Ei, the square of their ratio. And we found that this was equal to 4n1 n2 over n1 plus n2 squared. And similarly, for the reflectivity R, we found that R is the ratio of ER over EI, and we also found this, and we saw that this was equal to n2 minus n1 over, it was n1 minus n2. Let's fix that. It was n1 minus n2 over n1 plus n2, and it was a mod square of it was a square of this. So we found the reflectivity and transmission coefficients, and something very interesting was that, of course, T plus R must equal to 1. This is just energy conservation, but also that the sign of the reflection, so the sign of R changes depending on if n1 is greater than n2 or if n1 is less than n2. So and we discussed this in some detail. Today what we want to do is that today we want to generalize this. So basically what we want to look at, so today we wish to generalize this to any direction of propagation. I mean, last time we only looked at normal incidence. Today we want to look at any direction of incidence. So we want to look at incidence at a general angle. So more specifically, what we're saying is that you have some interface between two materials of, let's say, refractive index n1 and n2. This is the surface normal. Okay, this is the surface normal n hat, and essentially what we're saying is that we have some incoming radiation, and this incoming ki makes an angle theta I with regards to the surface normal. There's some outgoing radiation which makes some angle theta r. This is kr, and then there's some transmitted radiation which makes an angle theta t with a wave vector kt. And basically what we want to find is how much light is transmitted, how much light is reflected, what does the angle do, how is it different from the case of normal incidence, and what physics and what applications can we draw from this. One very cool thing that I promise you'll be able to understand by the end of this lecture is, for example, how Polaroid how polarized glasses work, why are sunglasses polarized and why that's an interesting thing, so on and so forth. Two definitions that we'll need. So two useful definitions that we'll need for this lecture. The first definition would be what is known as transverse electric EM waves. So what's a transverse electric EM wave? A transverse electric EM wave is a wave in which the electric field is perpendicular to the plane of incidence. What does that mean? That means that if you have, so this is your surface, this is your interface, and this is your incoming plane wave, right? Now, the electric field is orthogonal to this plane. So basically, if this is the plane, if these define a plane, and if the electric field basically points out of the screen, that's transverse electric. And if the electric field is in the same plane, that's transverse magnetic, which we'll introduce now. So light which is in which the electric field points perpendicular to the plane of incidence, it's called TE polarized EM waves. And so this the second definition that I wanted to introduce was, of course, it's not obvious, but still, it's transverse magnetic. ठीक है? और transverse magnetic क्या होता है? Transverse magnetic is the case when the electric field is parallel to the plane of incidence. ठीक है? यानी कि if you go to the diagram on the previous slide, the electric field is in the same plane as the plane of incidence, which means that the magnetic field in this case is in fact perpendicular to the plane of incidence. ठीक है? To the plane of incidence. So such light are called TM polarized EM waves. ठीक है? So TE and TM are two very special cases. If I just quickly draw them out for you one more time. So basically, this is your interface. This is your normal. So let me just extend this to here. So this is your incoming wave vector, this is your reflected wave vector, and this is your transmitted. This is Ki, this is Kr, this is Kt, right? And if, for example, B is in the same plane as these three vectors, so if this is B incidence, right? And this is refractive index N2, so this is TE polarized. And if in fact it's something like this, where this is your interface, this is refractive index N1, this is refractive index N2, you have incoming electromagnetic radiation, you have some reflected electromagnetic radiation, and you have some transmitted electromagnetic radiation. So this is your Ki, this is your Kr, this is your Kt. And now, if in fact it is the electric field which is in the same plane as these three other vectors, then you have EI here, and of course this is 90, this is also 90. And so now B points perpendicular, right? So what you have is transverse magnetic polarized electromagnetic radiation. So in analogy to how we did it last time, once again, let's write down the expressions for the incident electromagnetic radiation. So the incident electromagnetic radiations, meaning the incident solutions to the wave equation in material with the refractive index n1 would be, so EI of RT would be E sub naught I. This is a vector. Let's give it a vector. E to the I of kr minus omega t, and the corresponding B field, B incident of RT would be equal to B naught I e to the I of kr minus omega t, which is just equal to 1 over v1, where v1 is the velocity in medium v1 of k hat crossed with the incident electromagnetic radiation, right? So if that's the incident electromagnetic waves, the well, we might have some reflections. So the some reflections at angle theta r, so they're reflected. Components of the electromagnetic waves, these would be some ER of RT should be equal to some E naught reflected e to the I of kr minus omega t. Okay. Now just to highlight this a bit, this k would of course be okay. I'll just write it after I write the expression for B. So BR of RT would be 1 over V1 of K crossed with ER, right? The full wave ER. Now in general, this wave vector would be the reflected wave vector. This wave vector would be the reflected wave vector. And this wave vector would be the incident wave vector. This wave vector would be the incident wave vector, right? Even if their magnitudes are the same, their directions are different, right? Because the incoming and outgoing wave point in different directions, right? So we have an interface, and we have an incoming k sub I, and we have an outgoing k sub I, and we have some transmitted k sub t. And so since we've already talked about the transmitted light, well, you can write down the equations for the transmitted light. So the transmitted electromagnetic waves would be, so ET of RT become equal to E naught T e to the I of kr minus omega t, and of course this is k sub t, and correspondingly the transmitting B field of RT becomes equal to 1 over V2 this time, because this time we are now in material 2 of KT hat crossed with ET, the vector. Now if that's alright, then I want you to notice that, so we have our three expressions for the electric field. Now in material V1, in material with refractive index n1 and as well as the material with refractive index n2, in every case the velocity, the phase velocity we've seen is equal to omega over k, right? Which is equal to, that's 2 pi f over 2 pi by lambda, so that is f lambda, right? Now that just implies that omega is equal to kV, both in material 1 and in material 2, right? Now you see, the frequency, angular frequency remains the same across the interface. So the frequency is the same in medium 1 and medium 2. The frequency is the same, but the refractive indices in general can be different. So the velocities can be different. So in general then, what we expect is that omega is a constant. But the right hand side, so omega is equal to kV. Well, in one case you would have k incident times v1, which would be equal to k reflected times v1, which would be equal to k transmitted times v2. Now there are multiple ways to think about why the frequency remained the same across the interface. If you believe me when I say that the velocity should be different because the different materials have different permittivities, so the so the speed of propagation is different. But we know that the speed must be the product of f and lambda. So why did f not change, keeping lambda constant? Well, the reason for that is that one reason you can say is energy conservation. We know that photon energy is E equals hf. So so f remains the same, and the energy of the photon remains the same in both materials. That's one way to think about it. Another way to think about it is that if the frequency starts to change, then you would get a piling up of waves at the interface, and that would be a very non-physical thing. So let's say if you have a source emitting at 100 hertz and only 50 hertz was passing around the interface, then what about all these other waves that are getting accumulated at the interface, right? That'll be a very non-physical kind of a situation. So that's why the frequency must remain the same across the interface. Of course, there are non-linear ways of changing the frequency also, but that's a separate topic. More importantly, then the wavelength compensates. But this product, the product of kt v2 ki v1 ki v1, this product remains the same. ठीक होगी बात? So then if we consider the plane wave like E naught I equals e to the I of ki minus omega t, then let me just explicitly lay down my axes. So let's say that the vertical axis going downwards is my z-axis, this is my x-axis, and this pointing out of the plane of the page is the y-axis. Now if we draw an interface like that, so the interface is taking place along the z-axis, right? If you match from the right, and if you have your incoming wave coming in and you have a transmitted wave here and some reflected wave here, so this is k incoming, then the interface is z is equal to 0. So the interface is z equals 0. We can define it to be z equals 0. So we have a plane wave incident at, so this is a plane wave, and our plane wave is incident at z is equal to 0. So the interface itself is of course the xy plane. Right? If you have an interface that is z is equal to 0, your interface itself it's a flat interface, it's the xy plane. Achha. Now if you go to last time and if you look at the boundary conditions we had, so if you go back last time, so our boundary condition 3, I believe, this was basically that E parallel 1 was equal to E parallel 2. This was the boundary condition, and this basically implies that E parallel incident plus E parallel reflected is equal to E parallel transmitted. ठीक है? Just a superposition of incoming in superposition of electric fields in medium 1 equal to the parallel components of the electric field in medium 2. Now parallel to what? Well, parallel to the interface, which of course means the xy plane. So we can write this as, so E incident parallel e to the I of k incident dot r is just the position vector minus omega t, plus E reflected parallel component e to the I of k reflected dot r minus omega t, plus E transmitted, plus नहीं is equal to, right, जो अभी हम लोग पे बाउंड्री कंडीशन लिखी है, so equal to E parallel t e to the I of kt r minus omega t, right? So this is our condition at z is equal to 0, ठीक है, for the parallel components using our boundary conditions. Now you see these boundary conditions, this must be true for all x and for all y at z is equal to 0, right? Otherwise you would have different phases as soon as you change x, and your equality will break down. So what this basically implies and what this necessitates is that, and this is very important to understand because this will actually form the basics of all of geometrical optics, जिसके laws हम अभी derive करेंगे. So this basically necessitates that ki r must be equal to krr must be equal to ktr at z is equal to 0, right? If you think about this, this condition must be true because you have a plane wave incident, and the equality between E parallel incident, E parallel reflected, and E parallel transmitted must hold at all points x and y at the interface. So this equality must hold. So if we write it down more explicitly, what this is basically k sub x incident x plus k sub y incident y equal to k sub x reflected x plus k sub y reflected y equal to k sub x transmitted x plus k sub y transmitted y. ठीक है, all of these things must be equal to each other. So this is true for all x and y at z is equal to 0. So since this is true for all x and all y independently, ठीक है, so essentially what this means is that you have two equations here. One is that so one is that k sub xi is equal to k sub xi, which is equal to k sub xt, and the other is k sub yi is equal to k sub yi is equal to k sub yt. ठीक है. Now and I borrowed this argument from Griffiths, which is our textbook which we're following, which is that if you now orient your axis, so consider this. If you orient your axis such that the plane of incidence, such that, I'll go to the next slide. The plane of incidence is the xz plane. This is just hypothetical, yeah. If the plane of incidence is the xz plane, then kyi is equal to 0 necessarily. There's nothing special about this. अगर कोई और केस ले लें कि such that if the plane of incidence is the yz plane, then kxi is necessarily 0. लेकिन if kyi is 0, अगर हम xz plane में incident है, that also means that kyi is equal to kyi is equal to kyt is equal to 0. So what that means is that the reflected and transmitted EM radiation is all in the xz plane. Okay, and this is very important because what this does is that it actually gives you the first law of geometrical optics, right? So what this gives you is the first law of geometrical optics. And what's that? Well, the law is that the incident, the reflected, and the transmitted wave vectors all form a plane, right? And this plane also includes the surface normal. Now you might think कि ये तो बड़ी obvious सी बात है, लेकिन ये नहीं थी obvious सी बात, क्योंकि ज़रूरी नहीं था कि ये होता, right? तो ये like the fact that this happens and we can actually see that, I believe is really cool. And of course at the back this is just coming from Maxwell equations. So essentially you can imagine if you have a ray of light, basically if you have a line of light, as we looked at our propagation vector, the transmitted, incident and reflected lines would all form a plane. Okay? And that's a beautiful thing if you think about it. Now we can actually take this a step further. If you notice that, so notice that we know that k sub x is equal to k sub tx is equal to k sub rx, right? The x components are all the same. So if you go back to the figure on the last page, that basically implies that k sub incident sine of theta I is equal to kr sine of theta r, which is equal to kt sine of theta t. ठीक है? But we also know that Ki V1 is equal to Kr V1. So we know that the magnitude of Ki is equal to the magnitude of Ki. So Kr is equal to Kt. So that must mean that sine of theta r must be equal to sine of theta I. So that means that theta I is equal to theta r, and this is nothing but the second law of geometrical optics. Second law of geometrical optics, which is that the angle of incidence, let's write a new line. So the angle of incidence is equal to the angle of reflection. I mean, you probably knew this fact before, but now you know why, right? So if you have an interface and if you have electromagnetic radiation coming in, the electromagnetic radiation which reflects is always reflecting at the same angle, and this is true for all polarizations, and this is true for all wavelengths of light, irrespective of whether it's a gamma ray, an X-ray, a microwave, or infrared, or whatever. So that's a very cool fact if you think about it. So that's the second law of geometrical optics, and now we go to the third law of geometrical optics. So we have also seen, we can basically extrapolate that K sub incident times V1 is K transmitted times V2. So K transmitted is equal to V1 over V2 K incident. But the higher the velocity, the lower the refractive index. So this is equal to N2 over N1 Ki, where N is the refractive index, right? So what this implies is that if you take our equation, which was Ki sine of theta I is equal to Kt sine of theta t, then Ki sine of theta I is equal to N2 over N1 Ki sine of theta t. So what this means is that N1 sine of theta I is equal to N2 sine of theta t. Okay? And this is of course something you're very familiar with. This is one way of deriving it. This was of course Snell's law of refraction, right? And this is how you can derive it very elegantly. So this of course is the third law of geometric optics, right? The third law of geometrical optics, which is that sine of theta t is equal to N1 over N2 sine of the angle of incidence. Okay? So the first law tells you that the incident, reflected, and transmitted light from a plane. The second law tells you that the angle of incidence is equal to the angle of reflection. And the third law is Snell's law, that N1 sine theta 1 is equal to N2 sine theta 2. Okay? So these are the three fundamental laws of geometrical optics, right? So now we can actually go on to if this is all good, and if we ever do take a course in optics together, then there's a lot more we can extrapolate from this and go on to lenses and so on and whatnot. But now I think we should go back to our original problem, which we started off at. And this, of course, was just that we have an interface with refractive index n1 and n2. This is our z-axis, this is our x-axis, and this is our y-axis pointing outside of the plane of the paper, right? And this is our surface normal. We have incoming electromagnetic waves here, outgoing electromagnetic waves here, and transmitted electromagnetic waves here. Now, one thing we know from our boundary conditions, which we've just seen, is that, and this is what we use to get all the laws for geometrical optics, is that K incident R is equal to K reflected R is equal to K transmitted R. Right? And of course, what we really want to find is the incident electric field and the reflected electric field and the transmitted electric field. And of course, we want to find the incident, the reflected magnetic field and the reflected and the transmitted magnetic field in terms of the incident. So in addition to this equation, which we will continue to need, well, what else do we need? Well, we need our boundary conditions. Once again, at z is equal to 0. Well, what are those boundary conditions? To start off, well, the first boundary condition, we know that the permittivity of the first material times the orthogonal component of the electric field is equal to the permittivity of the second material times the orthogonal component of the electric field, right? We derived this last time. This is the same, right? I mean nothing else should change. So this is the same. So what this implies, well, what's the total initial electric field? Well, the total initial electric field is nothing but E1 times E naught I e to the I of kr minus omega t plus E naught I e to the I of kr minus omega t, and this is equal to E2 times e to the I of kr minus omega t. Okay. Sorry if I've been a bit lazy, and so this is the orthogonal component. Of course, sorry, and let me just correct this. So there's a bracket here, and then there's Et ka orthogonal component here. Okay. Now, this is where you have to listen to me a bit. So we know that KIR is equal to KRR is equal to KTI. Okay, we determined this by the invariance in x and y at z is equal to 0 at the interface, because we had a plane wave. Now look at this term. This term is E naught I perpendicular e to the I kr minus omega t. Now KR, what K? Well, this is KIR, this is K reflected R, this is K transmitted R. Okay. Now KIR is equal to KRR is equal to KTR, and omega t is just the time, and of course we're talking about everything at the same time. So if you divide by all the exponential factors, because all the exponential factors are actually equal, So you can simply divide by the exponential factors. All the exponential factors are equal. So what you're just left with is something really simple, which is that E1 times E naught incident perpendicular plus E naught reflected perpendicular is equal to E2 E naught transmitted perpendicular. Now the perpendicular direction to the boundary is just the z-axis, is it not? Right, it's just the z-axis. So in actuality what we have is E1 times E naught I plus E naught R z component is equal to Et times E naught transmitted z component, right? Because the perpendicular is just the z component. So our first boundary condition actually gives us this, which we will call equation 1. This is equation 1. Okay. Now okay, I'll just write it numerically 1. Now our second boundary condition is that the perpendicular component of the B field in material 1 is equal to the perpendicular component of the B field in material 2. So once again, the perpendicular component is nothing but the component along the z-axis. So B naught I plus B naught R z is equal to B naught transmitted along z. And this is of course our second condition. Now the third condition that we have will basically be that, so I'll just label this as 3. So we know that the parallel component, and we've already discussed this, should be the same on both sides, right? So E1 parallel should be this equal to E2 parallel, but the parallel component is the xy plane. So what we have is that E naught incident plus E naught reflected, okay? The parallel component is the xy is equal to E naught transmitted xy, right? And so this is our third. Let me just use the same convention we've been using. This is our third boundary condition, and our fourth boundary condition, so is that 1 over mu1 times the perpendicular component of the B field in material 1 is equal to 1 over mu2 times the perpendicular component of the B field in material 2, right? And so the perpendicular component is nothing but the xy plane. Now look, the parallel component to the electric field is the xy plane, and since the magnetic field is pointing perpendicular to the electric field, so the parallel component to the magnetic field is the z-axis, and the perpendicular component to the magnetic field is the xy plane, right? So this just means that 1 over mu1 times B naught incident perpendicular plus B naught reflected perpendicular xy is equal to 1 over mu2 times B naught transmitted perpendicular along the xy plane. Okay, and of course these are two separate equations, one for x, one for y, and so this and these are also two separate equations, one for x and one for y. So now this is our boundary equation 4. So now we have 4 boundary conditions, right, for oblique incidence. So so now we basically have everything that we need to solve. So what I will do is that we will solve for TM polarization, and we can do TE polarization as a homework assignment. So when I say that we will solve for TM polarization, what I basically mean is that this is your interface, these are your axes, y is pointing outside the plane of the page, this is your surface normal, and this is your incoming k vector, this is your refracted k vector, and this is your reflected k vector. Your incoming k vector is coming in at an angle theta incidence, your reflected wave vector is going out at an angle of theta reflected, and this is making an angle theta transmitted. This is k sub I, this is k sub r, this is k sub t. Talk about learning by repetition. Well, we've done quite a lot of that. The electric field, so we have TM polarization, so the electric field, so the magnetic field points perpendicular to the plane of incidence. That means that the electric field is within this plane, so the electric field is normal to the k vector, so the electric field would point somewhere like this, or it would point the other way, but it's the same thing. So the electric field would be EI pointing like that. Okay. After transmission, you will have some transmitted electric field pointing like that, and after reflection you will have some reflected electric field pointing like that. Now this is the setup of our problem. So now let's start using our boundary condition. So using boundary condition 1, we know that E1 times EI plus ER z component is equal to E2 times E naught transmitted ka z component. Now question is, how do we find the z component, right? So let's find E1 EI z. Okay, let's find E1 EI. So I'll just write it down here again. So we want epsilon 1 EI z component. Now let's just lay down the geometry of this. So if this is my z axis, and this is my x axis, if you notice that if this is my if this is my incident electric field vector, then this is the triangle that it follows. This angle is theta incident, this angle is 90, this angle here is 90 minus theta incident, and this angle is 90 plus theta incident, and as a result this angle is 90 minus theta incident. Now what we're interested in is the z component. So the z component is the cosine of this angle. So then this becomes equal to minus epsilon 1 E naught incident cosine of 90 minus theta incident. Okay, and cosine of 90 minus theta incident becomes equal to E1 E naught incident sine of theta incident, which becomes equal to minus E1 E naught incident sine of theta incident. So, and of course you get a minus sign because it points in the minus z direction, right? So by similar calculation, it is possible to show that E1 E naught reflected z component is equal to epsilon 1 ER sine of theta r, and you can also show that E1 epsilon t z component is equal to minus epsilon 2 minus epsilon 2 E naught transmitted sine of theta transmitted, right? So the first boundary condition finally gives us that the components are related as minus epsilon 1 EI sine of theta I plus epsilon 1 ER sine of theta r is equal to minus epsilon 2 ET sine of theta t. And this is an important equation, and we'll call it equation A. Now let's go on to the second boundary condition. इसको हमने boundary condition 2 कहा था, ठीक है? The boundary condition 2 was that BI plus BR z component is equal to B transmitted z component. But you see, all of these are equal to 0 as the z component of B is 0 as we have TM polarized electromagnetic waves. If instead we were doing TE polarized, then of course this would have been non-zero, right? As we are doing TM. Sorry, I think I just repeated that. Now, moving on then, the third boundary condition boundary condition 3, what this basically gives us is that so EI plus ER XY is equal to E transmitted in the xy. Now we have TM polarization, and the y direction is where the B axis points, right? Sorry, where the B field points. So in fact, what we have is that E incident y is equal to E reflected y is equal to E transmitted y is equal to 0, right? Once again, because it's TM polarized. Guys, like this will not be the same for TE polarization, but for now it is. But what's the x component? The x component becomes, so the x component becomes by making a similar triangle to the one we just made before, what you can find is that E incident x actually becomes E incident sine of 90 minus theta incident, which is equal to E incident cosine of theta I. Use the exact same triangle we used before, but this time we want the x component, right? So it's the sine rather than the cosine we had for the z component. Similarly, let me just draw it out for you anyways, because I think it's, forgive me for that line. So we have z, we have x, and we have our incoming electric field. This angle is 90 minus theta incident, and we want the x component, so we take sine of 90 minus theta incident, right? So by the same logic then, E reflected x component becomes E reflected cosine of theta r, and E transmitted x component becomes E transmitted cosine of theta t. So what we get is that EI cosine of theta I plus ER cosine of theta r becomes equal to ET cosine of theta t. Okay, and we will call this equation D, because this is another condition we get using the third boundary condition. Okay, and now using our using boundary condition 4, boundary condition 4 was that 1 over mu 1 times B incident plus B reflected, their x and y components, is equal to 1 over mu 2 B transmitted x and y components. Okay, so we know that well, x component of B is 0, because it's, once again, it's TM polarized, so we only care, so all the bx's are 0, right? So we only care about the y components. So we can write an equation for that actually. So B incident over mu 1 plus B reflected over mu 1, their y component is equal to B transmitted over mu 2, its y component. We know that mod B is equal to mod E over the velocity. So we get a third and final equation which we can use, which is that EI over mu 1 V1 plus E reflected over mu 1 V1 is equal to E transmitted over mu2 v2, and this is what we'll call equation C. Okay, so now in total, equation A, equation B, and equation C give us three equations that we can use, right? So equation B is on the slide before, and equation A is on the slide before that. So I'll just put a temporary break here because we have all we need, and now we just need to plug in a couple of formulas in order to get to where we want to get to. So we know that using the second law of geometrical optics, we know that theta I is equal to theta r. So if you substitute this in equation A, what you get is that minus epsilon 1 ei sine of theta I plus E1 ER sine of well, it's sine of theta r, which is the same as theta I. So I can just write sine of theta I is equal to minus E2 E transmitted sine of theta transmitted. But we know that now, we also know now using Snell's law, which is the third law of geometrical optics, that sine of theta t over sine of theta I is equal to the ratio of the refractive indices. So this is equal to n1 over n2. So to summarize, then we can rewrite this equation as negative epsilon 1 ei plus epsilon 1 er is equal to minus epsilon 2 n2 over n1 times E transmitted. So to summarize, then ei minus er is equal to E2 over E1 sorry, this was n1 over n2, so n1 over n2 times E transmitted, and this is the first equation we'll need. Similarly, now if you use equation B, where equation B basically told us that ei cosine of theta I plus er cosine of theta I, because theta I equals theta I, is equal to et cosine of theta t. Now if we use this equation, then we can basically write that ei plus er is equal to et cosine of theta t over cosine of theta I. Now if you define alpha to be equal to cosine of theta t over cosine of theta I, and if you define beta to be equal to E2 n1 over n2 n1 over epsilon 1 n2, and So this is our second equation. So now we have two equations which relate the amplitudes of E1, ER and ET. So we have all we need to express ET and EI in terms of EI, right? So we have two simultaneous equations. So if we add them, so what you get is that E naught transmitted becomes equal to 2 over alpha plus beta times E naught incident. And if you subtract them, then what you find is that E naught reflected becomes equal to alpha minus beta over alpha plus beta times E naught transmitted. So these are two extremely important equations. So this tells you the component of the electric field that's transmitted, and this tells you the component of the electric field that's reflected. Now together these are called the Fresnel equations, and these are very useful equations for understanding what happens to electromagnetic radiation when it's incident at a boundary. So now not only do we understand how much light reflects or transmits when it hits when it goes from one dielectric to another, we also understand what happens as a function of angle. And very interesting things happen when alpha becomes equal to beta, so on and so forth. So of course everything that we've done is so this is for TM polarization. And so so these are the Fresnel equations for TM polarized light. Now you will of course get two more Fresnel equations. So you get two more Fresnel equations for TE polarized electromagnetic waves. And the real cool thing is that so this works for X-rays, it works for gamma rays, it works for microwaves, it works for the whole spectrum. I mean, imagine, think about it. If you have any TM polarized light, then the transmitted light will always be 2 over alpha plus b times the incident light, like the incident electric field, no matter what wavelength or what frequency it is. So as long as you know the alpha, which is I mean alpha is just a geometric thing, it's the ratio of the cosines, and as long as you know beta is actually where the material part comes in. So for example, how light, for example, why does light bounce off of X-rays? Why do X-rays bounce off bones but they don't bounce out of skin, off of skin? Well, and which is why we can image. Well, it's beta, right? I mean, alpha is the same for visible light and X-rays in an X-ray room, but the difference is beta, and that beta allows you to image the bone structure using X-rays. And similarly, I mean, this is why microwaves can travel and reflect off what they reflect off, so on and so forth. So the Fresnel equations are very powerful equations, and they tell you a lot about how electromagnetic radiation behaves off of different interfaces. And just like we had for normal incidence, if alpha is greater than beta, then the reflected and incident light are in phase, and if alpha is in fact less than beta, then the reflected and incident electromagnetic waves are 180 degrees out of phase. When we did the case of light at normal incidence, we basically said that when the second refractive index is greater than the first refractive index, then light is 180 degrees out of phase. Now we're basically saying that if the second if alpha is less than beta, you get that case. But it's the same physics. You can actually see that if you plug in theta is equal to if you plug in the theta is equal to 0, which is the theta for normal incidence, because we're taking angle from the normal, you actually recover the same equations we had last time. Now we'll spend a few more minutes on this in the next lecture, because I want to do some special cases and I want to talk about the amount of light that's transmitted and reflected, because I think this deserves a bit more attention. So we'll discuss these a bit more. We'll talk about the amount of intensity, we'll talk about something called the Brewster angle, so on and so forth. And then we'll go on to the reflection and transmission of light from conducting surfaces. So this is basically a completion of whatever we wanted to say of electromagnetic waves incident on dielectric interfaces. And I hope, we've used the boundary conditions quite a lot. It's basically the same boundary conditions we derived in the chapter of electrodynamics. It's just that we first tailored them to the case of dielectrics, and then we've had to do geometry specific considerations. So I hope this is all clear, and if it's not, then I'll be happy to take any questions online. Thank you very much, and I will see you in lecture 21. Thank you.